Hope everyone had a good weekend and are excited to get back into learning more about quantum algorithms. This week and the next week are where we are going to really focus on the core material of solving quantum algorithms for differential equations. In last week's fireside chat that we had with Andrew Childs, Harry Grovey, and Herman, one of the things that they discussed was how we need efficient data access models. And that is having efficient data access models is like one of the key challenges that we need to solve if we want to develop better and better algorithms for solving differential equations on quantum computers. And so today's talk by Dr. Amit Surana is going to address, was one way to address this question. And we're very excited to welcome him. Today's talk is on developing efficient quantum access models for sparse structured matrices using the linear combination of things technique. And for this, we welcome Dr. Amit Surana from the RTX Technology Research Center. Amit is actually a longtime collaborator and a friend of mine, and I'm very excited to welcome him to this program. Amit is a principal technical fellow at RTX Technology Research Center, and he has 16 plus years of R&D experience in the areas of nonlinear dynamical systems, controls, machine learning, autonomy, and quantum computing, with a broad range of applications in the aerospace and defense industries. And he has authored over 80 plus peer-reviewed publications, and he has 10 patents granted and 20 plus patents pending. And he has won several awards and honors. And he brings us like this rich expertise from like classical computing and AI and machine learning. And he is also now bringing in his expertise in quantum computing and tying it all together to really solve problems in aerospace and defense. And we're very excited to welcome him into this program. Thanks for coming, Amit, and over to you.
Great. Thank you so much for the nice introduction and inviting me. Thanks to all the organizers for inviting me for, to this exciting seminar series. So let me share my screen here. You can see my presentation.
Yeah.
Okay. So yeah. Great. Yeah. So I guess I'm really excited to talk about this recent work we have been jointly doing with Abhinay on this efficient access models for sparse structure matrices that often arise in a lot of applications, especially in PDEs, ODEs, which is the focus of this summer program. And so let's get into that. So I'm going to start with the objective and the background on why we need this approach. And Abhinay already alluded to this. And we will introduce this concept of sigma bases, which will be our things, which we are going to combine to get efficient representation and data access models for sparse structure matrices, right? And as you'll see, these bases are formed from non-unitary operators. So we have to do a little work, use the concept of unitary completion to construct efficient circuits to implement observables based on those operators, which are what is required, right, in quantum algorithms. We'll also compare this approach with other related methods like unitary dilation, you may be familiar with, and Pauli basis, LCU, which is the most common approach used in this context. And then we'll apply this framework to, some variational and fault tolerant quantum algorithms, and then, conclude the talk. Okay. So as you may be from many different backgrounds, but probably, you have kind of exposed to partial differential equation or ordinary differential equation, right, which arise in many engineering and science applications. Some of the PDEs are listed here in this picture, like Navier-Stokes, which describes the fluid flow, the heat transfer, PDE, reaction diffusion equation, chemical kinetics, and so on, right? So often these PDEs cannot be solved, or seldom these PDEs can be solved analytically, right? So you have to really rely on numerical techniques. And in that context, the solutions of these PDEs or these, after discretizing them, can be often cast into a system of linear equation, right? So the matrix A you get from this discretization is not something arbitrary, right? It has a very special structure, and it's often sparse, right? So the structure could be, it's a diagonal matrix, it has blocks, block diagonal, it could be banded, and it could be like tuplets and so on. And we'll see several examples throughout the talk. So As you know, right, quantum linear systems algorithm provide like HHL, you may have heard about, and its variants provide, a promising approach in terms of it could lead to an exponential speed up in solving these equations and generating the solution of these linear systems. But the success of these methods often rely on the assumption that there are efficient quantum access models, like how you're going to load this matrix, which is non-unitary, into a quantum computer, right? And so the objective of this talk is to see if we can use the structure and sparsity to gain efficiency in such data access models, right? So with that in mind, we are going to work with LCU decomposition, which is a versatile data access model. And there was a talk about this, I think, a week or 10 days ago. So you're probably familiar with this concept. But say you are given a matrix A, which size capital N, and we'll assume that's a power of, it's to the power N for some small integer, for some integer N for convenience, right? So its linear combination of unitary decomposition is defined by the equation below, where we are writing A as a sum of unitary matrices, where these coefficients alpha in general can be complex, and these UL are unitary matrices, and NL is the number of LCU terms, right? So the most common approach for LCU decomposition uses this Pauli basis, which are these Pauli matrices, which you have probably seen many times by now, like the identity sigma x, sigma y, sigma z, or xyz, whichever notation you're familiar with, and these are listed here. So the terms UL are formed from the tensor products of these. And since these are themselves unitary, this UL is a unitary operator. And so if you can decompose A in terms of these unitary operators, and then it can be used as a data access model in a variety of contexts, like variational quantum algorithms. And I'll show an example like for VQE, and we'll see another example of variational quantum linear solver later in the talk. And also in fault-tolerant algorithms, block encoding, which I guess you also heard a couple of weeks back, LCU will an important role in block encoding the matrices, which is again a fundamental construct in a lot of fault-tolerant algorithms like quantum signal processing, quantum value singular transform, and so on. So let's see how LCU decomposition can be used in variational quantum algorithms, right? So say we are given the problem of computing ground state of an Hamiltonian H, where H is an Hermitian operator, right? It's not a unitary operator, and we want to compute its ground state. So variational quantum eigensolver uses an ansatz psi theta and classically optimize the parameter theta, so to minimize this energy E theta, right, which is lower bounded by E0. So if you minimize this, you would get to the minimum ground state of this Hamiltonian. But H is non-unitary, right? It's Hermitian, but it's non-unitary, so you cannot directly load it on a quantum computer and work with it. So one approach is you do a LCU decomposition, so write H as a sum of unitaries, and then you can compute this inner product, which you need to minimize classically as a sum of these terms, and each of these terms can then be estimated through the Hadamard test, which you have seen, right? So you have a real part and imaginary part circuits for Hartas. This circuit is just shown for the real part, right? So the thing to note is that number of such circuits you're going to need to compute this expectation value, scales linearly, right? So the larger, the more the tests you want to do. And we like to have decomposition or representation where NL is as small as possible, right? So you can be more efficient in computing these expectation operator. So let's move to fault-tolerant algorithms. So block encoding, as I mentioned, is a common construct in which you take a non-unitary matrix and embed it as a block in a large unitary matrix, as the name suggests. And if you take an ancilla system of this form, the action of U basically can be represented in this form. And since you're represented on A psi, you can post-select, and with some probability, you will get the desired outcome, right? Because ultimately, you want to apply A on some quantum state psi, right? So there are many different ways of block encoding, and we'll focus on LCU-based block encoding, which basically uses this prep and cell oracles. So the prep oracle prepares this initial state, which depends on the coefficients alpha k of the unitary LCU decomposition, and select operator essentially selects one of those unitary in the decomposition to apply to. psi k, and it can be shown that this circuit really prepares the action of a psi normalized by lambda, which you know by the terms of the LCU, the coefficients of the LCU decomposition. So as we'll see again, larger NL means larger number of LCU terms means increased quantum resources. You need more ancillas, more gates, and a bigger circuit depth to implement this associated circuit. So ideally, we want to get an efficient representation with reduced NL, right? So with that in mind, let's get back to Pauli basis LCU and consider some of its properties. So, you know, the ULs are formed from these sigma terms, the tensor product, and each of sigma I belongs to Pauli basis. And since these are unitary, the Pauli terms you can efficiently implement on a quantum device. And also in many applications like quantum chemistry, like I showed, computing the ground state energy, the Pauli decomposition of the Hermitian or the Hamiltonian is known by construction. So you get that for free. But in more general cases, like we would be interested in when we are solving PDEs, ODs, such a decomposition is not available, and you have to rely on numerical techniques. And there are many techniques which you can see in the paper listed below at the bottom of the slide, like trace formulas, so posing it as a system of linear equations, or more smarter ways of recursive approaches, right? But in general, as we'll see in many examples, the number of Pauli LCU terms, NL, can vary with the size of the matrix, right? So N, capital N is the size of the matrix, which is assumed to be 2 to the power N. So for diagonal matrix, the number of terms can scale either linearly or quadratically for diagonal and dense matrices respectively. And for sparse matrices, NL can in fact be more than the number of terms in A, which is like not ideal, right? So as we discussed, right, that larger NL means you need more quantum resources, either more circuit runs if you're working with the variational algorithms, like more Hadamard tests, or more ancillas, more gates to implement the prep and the cell oracles we discussed in the block encoding approach, right? And so that can become a key bottleneck in using LCU and can impact the advantage of many, quantum advantage in many applications, like when using HHL to solving linear systems. But what we want to show in this talk is that by using different bases or different things, we can obtain polylogarithmic dependence, right? So the number of terms depend polylogarithmically on the size of the matrix N, or polynomially on small n, right? And for not general, but for sparse structure matrices. So how do we do that, right? So for that, we are going to use this notion of sigma basis, which was introduced first in this paper by Halen, and then later extended in our work with Abhinaya. So this sigma basis includes the identity operator, the identity 2 by 2 matrix I, but some other non-unitary operator instead of sigma x, sigma y, sigma z. We have sigma plus, sigma minus, sigma plus minus, and sigma minus plus, right, which are listed out. So as you can see, these are non-unitary operators, right? And we are going to take the matrix A of interest, and we are going to do a linear combination of now non-unitary decomposition, which is analogous to LCU, but now the terms AL in the decomposition form from these bases elements which belong to the sigma basis, right? So these are non-unitary operators in general. And as we'll see through several examples, why we want to do it, because sigma basis will offer an efficient decomposition, like the polylogarithmic dependence of this NL on the size of the matrix for sparse structure matrices under certain assumption. But remember, these are non-unitary operators, right? So while we get a reduction in NL, that's great. It should not come at an expense of proportionate increase in quantum resources for actually implementing these unitary operators, right? So as we'll see, that's indeed the case. You can get this reduction in the number of terms without, excessive increase in the quantum resources needed to implement these operators, since they are non-unitary ones, right? Okay, so let's start with a simple example. If we have a 4 by 4 matrix which has just two non-zero entries here, and if you do a Pauli decomposition, you will need 4 terms to represent that. But if you use sigma basis, we only need 2 terms, right? And in general, we are going to show that the number of terms in a Pauli sigma base is always less than equal to the number of non-zero entries in A, right? Which is ideally what you would like to have in a efficient decomposition, right? So this is a very simple example, but next I'm going to show you several examples of linear, non-linear PDEs. We are going to work in 1 dimension because it's easy to go over, the the math, but these results do generalize to higher dimensions under certain assumptions. And you can see the paper I'm going to refer later in in detail for the details. Okay, so let's start with Poisson, which is an elliptic PDE. It's a second order PDE where your solution depends on space. So if you apply a central difference discretization scheme, you get a linear system of this form where A has this sparse and a structure, in the way that these 2 minus 1 minus 2 kind of repeats itself, right, in this matrix, right? So this is a nx by nx size matrix where nx is the number of spatial discretization points you use to discretize this PDE, and B is the right-hand side, which depends on this forcing function f, right? Okay, so for simplicity, let's assume nx is some power of 2 to the power s, where s is some integer. So now if we look at the structure of A, we can actually do a recursive decomposition. So A can be broken into these 4 blocks, and for a simple example of 8 by 8 matrix, I list these blocks. So A3, S is 3, and its upper and lower part have the same A2 matrix in there, and then there's these off-diagonal matrices D2 and D2, and this upper part is the transpose of that, right? You can see that there's a -1 and here, right? So you can break this matrix into these 4 components, and then using tensor product, you can write this AS in terms of AS minus 1, which are these 2 submatrices. So if you multiply I2 by that, you're going to get those 2 terms here. And then if you multiply sigma minus, you'll get the term here, because sigma minus, remember, has a 0, 1 at the bottom left here, and then sigma plus will give you this term, right? And the sigma S minus 1 itself has only a -1 here. And so it can be directly written as a tensor product. If you take sigma plus and multiply them as minus terms, you're going to get this, right? And so if you keep doing this recursive decomposition, take AS minus 1, apply same decomposition again, you'll get 2 DS minus 2 terms. And if you keep going, you'll reach to the last part, which is A1, which basically is this little matrix here, which you can write it as 2 times identity minus sigma 1 minus sigma plus, right? Again, sigma minus will give you -1 here, sigma plus gives you sigma plus here. So if you count how many terms you need, basically you are decomposing AS every time you generate 2 terms, and then in the end you generate this 1 term, so you get 2s plus 1 terms, which is 2 logarithmic on nx plus 1 terms, right? So it's the number of terms is actually logarithmic in the size of the matrix, which is what we want. So if you actually plot for different values of nx the number of nl terms, comparing sigma and Pauli basis, we know sigma basis gives you this logarithmic dependence. So this is a semi-log plot, while the Poisson equation, the number of terms actually increases linearly with nx, right? So again, by using the structure and the sigma basis, we have been able to achieve, logarithmic dependence on the size of the matrix compared to Poisson for Pauli. And for Pauli, we use numerical technique to obtain this decomposition using the reference I mentioned earlier in the talk, right? Okay, so this is one example, but you probably see that idea, like we take a matrix, we're going to break it into a recursive kind of structure. We'll have these off-diagonal terms for which we can write a tensor decomposition in terms of the sigma basis, and we'll recursively construct this sigma basis. So you'll see this structure again and again in other examples. So let's now consider heat or a parabolic equation. So now your U, or the temperature, depends both on space and time. Here the boundary conditions are Neumann boundary conditions, and this is the initial condition. Again, you use your favorite procedures to discretize in space and time. Here we used central difference to discretize the spatial part and the forward Euler to discretize the temporal part, and you get a system of linear difference equations where now solution depends on the grid point and the time. And then again, you can take all this system and embed it into a large linear system of this form, AU equal to B, where A can be represented as a sum of 2 matrices, A1 and A2, right? So A1 has this structure, A2 has this structure. Again, it's very sparse and kind of banded structure. So again, we assume that nx and nt are powers of 2, and we can again follow the same recursive procedure where we break as plus t into these smaller block Matrices, remember, there's no, if you look at this matrix, all are zeros on the upper right, so you have a zero here, and where ds plus t minus 1 is an identity, right? So if you're going to break it into blocks here, you're going to get one identity minus here, which is very similar. You got a minus 1 in the Poisson equation. So you can write it again as a direct decomposition over the the sigma basis, and then do a recursive expression to show that this A1 can now depend on log nt plus 1 term. Remember, every time you're decomposing, you're getting one term, so it becomes log nt plus 1. And then similarly for the A2 part, you can show that you'll get 4 log nx plus 6 terms. Again, the number of terms depend logarithmically on the number of spatial and number of temporal and spatial discretization points. So this is a plot again comparing Pauli and sigma basis. So with Pauli basis, again, the growth, so this is semi-log plot, growth is more than linear. So this black dotted line is x equal to y, right? So the number of terms actually increase more than linearly for Pauli basis, while it has the logarithmic dependence in the sigma basis, right? So this was an example of parabolic PDE, and so this is an example now of hyperbolic PDE, which is again a linear PDE, 1D wave equation. You can check out the paper for the details, but again, following very similar procedure, you can show that the number of sigma basis terms in its decomposition depends polylogarithmically on NT and NX. And again, it's much more efficient than Pauli basis, right? So these were examples of 3 classes of linear PDEs, which often arise in many applications. As I mentioned, these were all in 1D for specific boundary conditions, but the results generalize under suitable assumptions for other boundary conditions. And when you move to higher order, like second PDEs in 2 dimensions, 3 dimensions, and so on. Okay. So what about nonlinear PDEs? Again, I'll not have too much time to go into that, but when you're dealing with nonlinear PDEs, so for example, 1D Berger's equation, so the nonlinearity arises because of this U times U term here, right? So these nonlinear ODEs cannot be directly simulated on quantum computer, right? So you cannot take those nonlinear terms and directly implement. So one popular approach is Kalaman linearization, which basically takes these PDEs, you discretize in space, and then you do a Kalaman linearization, which basically transform this nonlinear polynomial PDEs, ODEs into a system of infinite dimensional linear ODEs, right? So you get a linear system, but the price you have to pay, it's infinite dimension. So you often truncate that in practice, and then you get a linear system of ODEs like we saw in previous examples, and then you can write a linear difference equation and embed it into a larger linear system. And you have to worry about error analysis, and you can see this paper, which was a seminal paper to introduce this idea, and probably came up in the fireside chat last week as well. Okay, so when you do this Kalaman linearization, the matrices you're going to get in your linear system are now much more complex. I don't have time to go into the details, but you can refer to this paper, and where we work out like how you can still apply sigma basis decomposition analytically or semi-analytically to derive sigma basis decomposition. So in this decomposition, it turns out that in the way we did it, the number of terms scale polylogarithmically with the number of spatial temporal discretization points, which is good, but we could only show polynomial dependence on nx, which was spatial discretization, and polynomial on the number of terms in the truncation of the Kalman linearization. But still, as when we plot this, we see the blue curves are the number of the number of terms in the decomposition for sigma basis. Red is the number of terms for Pauli. We can still see that the sigma basis decomposition, as you increase the order and vary the size of the grid points and x, and if you can have order of magnitude lesser number of terms, right? Like for instance, with nc equal to 2, you have less than 100 terms in sigma basis, while a Pauli basis may require more than 10 to the power 5 terms, right? So recently this result was improved by Rubin and his team, where they included these permutation matrices and added it to the sigma basis, which is again things, right? We're adding things to that basis, and they showed that by doing that, you can actually get polylogarithmic dependence both on nx and nt, right? Which is great. Like that's what we're looking for, and you'll hear more about this, I think, in a talk later in a week. So stay tuned for that, right? Okay. So So I've given you a lot of examples, right? Okay, there's so many PDEs, we can work out these decomposition, but like you have a problem, you're given A, how are you going to think about this type of decomposition? So I'll discuss now computational method, a general approach, how you can do that. And so the goal again here is that you are given a matrix A, you want to decompose it in terms of some of these matrices AL, which are formed from tensor products from your sigma bases, right? So let's start the most simplest case. Let's assume A is is a sparse matrix with only one non-zero entry, right? Everything is zero, only one place at location RC, there is a non-zero entry. So this theorem provides a simple procedure to construct the sigma basis decomposition, right? So basically you take your R and C, the row and the column, which is non-zero, you do a binary representation of that, two numbers. And then depending on at each of the location, the binary representation bit is 0 or 1, you're going to use these four sigma basis operators, right? And you insert them in the tensor product and you multiply that by the non-zero entry, you get one term sigma basis representation of that sparse matrix with one non-zero entry, right? So with that, say you're now given a general matrix A, which is sparse. So you can write that sparse matrix as a sum of matrices with only one non-zero entry, right? And then you can apply the previous theorem. So this shows that for sigma basis, or proves that, right? For sigma basis, if there is NNZA non-zero terms, you can have at most that many, you need at most that many terms in the sigma basis decomposition. Note that we haven't used identity, which is also part of the sigma basis decomposition in this construction, right? And so this may not be the most efficient decomposition. So in general, we propose a semi-analytical approach where you can mix analytical and this numerical technique, like we saw in several examples earlier. So you look at the matrix structure and you see some recursive telescopic pattern for which you can by hand write that analytical expression. And then there'll be some non-zero terms straying out like off diagonal for which you can use this type of numerical method, right? So again, there's no general procedure to get the most efficient decomposition, but by looking at the structure and using this numerical technique for representing sparse matrices, you can in practice obtain decomposition for sigma basis, right? So I'm going to move next to how we are going to actually implement these operators, but are there any questions we want to take now, Amit, or keep going?
Yeah, we can take a few questions. We have a couple of questions. Okay, maybe that. This is a question from Archana. Why does a quantum computer only take a unitary and not a Hermitian?
Oh, so like, the quantum computers evolve according to Schrodinger equation, right? Which is I d, d psi by dt, h psi, where h is the Hamiltonian. So the psi is e to the power minus ht, which is a unitary matrix, right? So just like in classical physics, everything obeys Newton's laws. In quantum physics, everything obeys the Schrodinger equation, and that evolution always is unitary, right? So anything you can implement on a quantum computer is based on those laws of physics, so it has to be unitary. Hope that answers the question.
Yeah, thank you. Another question from Sergio. So what are the conditions required for a matrix to be decomposable into unitary matrices?
Oh, so I mean, any matrix can be decomposed, right? The basis you're going to choose should have certain property in the sense it should be complete, right? It should be able to produce entry at any point on the matrix. So as long as it has that property and you can implement each of that term, as an unitary, you can decompose any matrix, right? So there's no special property. You can always do that as long as you have a complete basis.
Okay, that sounds good. One more question. What is the largest matrix dimension that can be numerically simulated?
Oh, that can be numerically simulated. So I guess you mean classically or quantumly? Well, quantumly, we are not there yet, right? But classically, these methods behave polynomially on N, right? The matrix solvers, like linear algebra solvers or linear matrix solvers, if you're talking about that. So you really need high performance computing to do that, right? And it depends on the problem, I guess. Like, what's the largest? I don't have, but I mean, do you know a large number? I don't know what's the largest matrix has ever been solved. I don't know.
I would say like billions. billions of
billions. Yeah.
Billions, yeah. So, yeah, we can keep going. Thank you.
Okay, great. Okay. So now the question is, okay, we are doing this decomposition using sigma bases. We are getting, efficient decomposition, a small number of terms. But now these sigmas are non-unitary, and as was asked, right, just a minute ago, anything you implement on a quantum computer has to be unitary, right, in form of gates, right? So how are we going to construct a circuit for this AL, right? And there are several options like unitary dilation you may be familiar with, but we're going to use this unitary completion idea, and we'll see why that's more efficient than using unitary dilation in a couple of slides later. So what is unitary completion, right? So you are given an operator U, which acts on a subspace W of linear vector space V, and it's a linear operator which preserves the inner product, right? So given W1, W2, the transformation of U applied on W1, W2 is same as the inner product between W1 and W2. So given such a linear operator, unitary completion of that is defined as operator U bar, which is unitary, which on the whole space V we are interested in, but whose action on vectors belonging to W is equal to the action of U, which is the operator you are given with, right? So that's basically you're taking that unitary operator, which behaves like unitary on a small subspace, and you are extending it or completing it to create this unitary completion, right? And then we define an operator UC, which is U bar minus U, as an orthogonal complement, and we'll see it's why is orthogonal, right? So such an unitary completion always exists, right? It may not be unique, but it always exists. Okay, so if we look at our basis elements, we can compute easily and show in the paper these are the unitary completions, right? So sigma plus unitary completion is sigma x. Remember, sigma plus has a 1 on the right hand side, sigma x has 1 and 1 on the the off diagonal terms, and that provides you the completion, and its orthogonal complement is just sigma minus, right? So you can work out very easily and show that these are the unitary completion and these are the orthogonal complement of those basis elements. But now our matrices are formed from the tensor product. So if you actually take the tensor product of the unitary completion for each of your term in your tensor product, you actually going to get the unitary completion of that operator, and then taking the difference of the unitary completion minus your original matrix, you get the complement. And this can all be proved. And another thing to note is that this AL, columns of AL are orthogonal to columns of this orthogonal complement, as the name suggests, and they provide this decomposition of the unitary, right? So with these properties in mind, we are going to define this operator UL, where we are embedding this U in that block. So it's like a block encoding with these orthogonal complements on the off-diagonal terms. And using these two properties, it's easy to show that UL is actually a unitary operator, and its action on an ancilla system gives you the action of AL on psi, right? Ultimately, you're interested in applying AL to some vector psi, right? By embedding it as a part of the unitary complement. So if you look at this, it depends on this ALC. So ALC, which is the orthogonal complement, is really doesn't have a closed form tensor product expression, right? So AL bar has a tensor product form expression, and AL is already given as a tensor product, right? So it's not convenient to work with when you're constructing circuit with this complement. So we are going to rewrite this UL as a product of two operators, which only depend on AL and AL bar, for which you know the tensor product decomposition. And also turns out that this AL bar is basically going to be a binary diagonal matrix, because sigma, if you take any term sigma in your sigma basis, sigma transpose always belongs to this set, and these are all diagonal matrices. So if you're going to multiply or take that tensor products, you're going to get terms only on the diagonal terms. So non-zero terms only on the diagonal. And so if you subtract that term, you're going to make this ones in the identity 0, and then those ones will appear here. So you're basically creating a permutation matrix, which is of size 2n plus by 2n plus 1, which can be implemented using only Pauli gates. And then the UL2 is essentially sigma x tensor product with AL bar. As you see, the AL bar only depends on these polybases, sigma, x, and I. So it's like very easy to implement the circuit for UL2, right? So we are going to implement the circuit of UL if by implementing this operator and this operator and taking the product of that. So what's the n control to gate, right? So to implement this permutation matrix, we're going to use this n control to gate, which essentially is a generalization of C0 gate or C2x gate, which is a to gate, or the CC0 gate, right? So essentially, it's an n+1 qubit operator that swaps two rows whose binary representation differ at the kth bit, kth being the target qubit, and then depending on whether you have an open or closed control on the other qubits, you're going to use a 0 or 1 and obtain the binary representation of that matrix is being swapped. So maybe just let's look at an example of CC0 gate. Here, the two rows being swapped have a binary representation 0, 1, 0 and 0, 1, 1. So the target qubit is Q2, so they differ at the kth qubit, which is the second qubit here, and then you see the other bits are same, and then there's an open control on Q2, so there's a 0 here, and then there's a closed control on Q1, so there's a 1 here. So these are the binary representation of those two rows which will get swapped by this circuit, right? Okay, so with that thing in mind, this is a pseudocode of how you implement UL, right? It's just a simple 5-step procedure. So maybe I'll walk through those steps through an example, right? So say we have n equal to 3 qubits, Q0, Q1, Q2. You are given a term in your sigma basis decomposition, which depends on sigma, which is tensor product of sigma minus I and sigma plus sigma minus. So the first step is we're going to compute the unitary completion of that. So we can just look at that table and see that sigma minus completion is sigma x, i's completion is I, sigma plus sigma minus completion is I, right? So we are going to now apply in the second step all the single qubit gates, which are sigma x here, and I on Q1 and Q2. And then we apply a gate x on A0. Remember that UL2 is sigma x times AL bar. AL bar is formed from these operators, and you need a sigma x operator on an ancilla qubit x here, right? And then we count how many times identity operator appears in this decomposition. It's 1. So we are going to use, step 4 is counting how many identity operators are in this decomposition. And then you're going to apply Cm minus k gate. So in this case, it's going to be a C2 gate because n is 3, k is 1. And we just saw, right, the C2 gate here. And then we are going to just see like at what location which operator appears, right? So we start with the 0th qubit here. We have a sigma minus belongs to this. So we're going to add a close control here. And then for identity, we don't do anything. And then the third operator is sigma plus sigma minus, which belongs to this. So we are going to add open control on Q2, right? And here is in very simple 5-step process, unitary completion circuit for your sigma basis decomposition, right? So I'll skip the proof. It's not hard to prove that this simple 5-step process actually generates and implements the UL correctly. It depends on certain lemmas, and you can look at the paper, right, for the details. Okay, so now let's compare the sigma basis with polybasis LCU, right, which is the most popular approach. But for that, first we need to understand what resources are needed to implement that n to gate, right? So this paper suggests a near optimal implementation of n controlled gate in terms of single qubit gates and C0 gates, and estimates a depth of almost order log n, where n is the number of qubits and the number of gates needed is order n with 1 ancilla qubit, right? So if you had a poly operator AL decomposed in poly, this is your circuit, which is simple because these are all unitary operators, right? But when you have a sigma basis decomposition, as we saw, right, this implements UL2. So these is like all the poly operators, X and I, and then you need another n to gate, right? Which is CMX, where M is less than the size, log of the size of your matrix, where M is actually n minus k, right? Where k is the number of times that identity operator appears. So based on this result, this table then compares, what it takes to implement poly versus sigma basis. So, so compared to poly basis, sigma basis, you need 1 more answer qubit here. The gates log n, which is log n coming from the implementation of this UL2 plus order M, which comes from the order N, right, where M is the CMX gate you need here. So to implement this N to Pauli gate, you need additional log N, less than log N, where N is the size of your matrix, and the depth increases by log N, right? But as you see, right, the number of LCU terms reduced exponentially. There is a slight resource overhead that you need one more qubit and few more gates with a slight increase in depth, but that's probably is not that significant, right? So overall, sigma bases really can, provide you an efficient decomposition and can be efficiently implemented, a goal we were striving for, right? Again, it depends on the sparsity structure and your application, right? This is not a general result. Okay, so unitary dilation. So what about unitary dilation, right? We talked about, right, like when we were taking these AL, these were non-unitary operators, and we had to embed them into block encode them in some way, right? And for that, we use unitary completion rather than dilation. So dilation is a more general concept than unitary completion. And without going too much into detail, we show in the paper that for our sigma basis, the unitary dilation approach to block encoding these component matrices is not that efficient, right? So if you, for example, take a single term AL equal to sigma minus, then you need 3 C0 gates to implement the unitary dilation versus just one C0 gate, right? And this is a general result which we show. So essentially, by using unitary completion for our sigma basis choice, it somehow is more efficient than using unitary dilation, though unitary dilation is a more general concept, right? Okay, so with that, I'm going to now, move towards how we use them in actual variational quantum algorithms and fault-tolerant algorithms, right? So we have the 2 ingredients, right? Given a matrix, we know how to decompose that matrix into sigma basis terms using either numerical or semi-analytical approaches, and we saw several examples of that. We know how to implement each of the AL terms. We just walked through how to construct the circuit, which is a simple 5-step process. Okay, so great. Now, in VQAS, in variational quantum algorithms, right, you're decomposing your matrix, and then you have to estimate terms of this form, like we saw in VQE earlier in the presentation, right? So the terms are typically of this form, but now our ALs are not unitary operators, but they are general sigma basis operators, right? So what we will do is we'll take the Hadamard test, which you may be familiar with, and we'll embed our approach to computing the unitary completion operator UL within that, and we'll be able to estimate these terms efficiently. So if you recall, our test, right, gives you the real and the imaginary part of this inner product, and these are the circuits, right? So this is the circuit to get the real part. You insert phase gate, you get the imaginary part, right? And so using that, this is a circuit to compute, the psi A1, psi 2. So essentially, if you look at, we have introduced one more ancilla qubit, and this top line is essentially this Hadamard test, and we have a controlled U. So this is our controlled unitary UL, but this is the unitary completion, which depends on the circuit construction we just went through, and this V and U are just constructing the psi 1, psi 2. So if you walk through this circuit, it's a simple algebra, right, to show that after you start with all zeros and you follow these steps, you end up with this state. And so if you measure these 2 ancillas, 0 and 1, and you compute how many times the probability of the pair 0, 0 and probability of the pair 1, 0, how many times 0, 0 and 1, 0 occurred after you sample the circuit many times, that is actually equal to the real part of this term we want to compute here, right? So we get the real part. If we introduce the phase gate here, just like we do here, we will get the imaginary part of that. So we know how to very easily compute a term of this form, right? Similarly, I'm not going into details, so you can look at the paper, but following similar process, you can also compute terms of this form here, right? Where M is now the operator like sandwiched between the application of UJ and UI, right? Okay, great. So let's see an example of how we use it, and we'll consider variational quantum linear solver. So just like HHL is a fault-tolerant algorithm, which you may be familiar with for computing a linear system, we are going to use a variational approach. There's a variational algorithm, BQLS, to solve the linear system. So we are interested in solving AX equal to B, And we have unitary given, which constructs our right-hand side, and we'll assume solution parameterized by a parameterized quantum circuit V theta. So theta is the parameter we're going to optimize using one of the cost functions. So these are the cost functions, which basically taking the action of A on your solution and then taking an error between your right-hand side and psi, right? And you want to minimize that error. So that can be written in terms of using this Hamiltonian. You can have a normalized or a normalized cost where you normalize by your solution to remove degeneracy. So often you may have heard about like variational quantum algorithms are affected by this barren plateau, which means it's very hard to optimize them. So for certain choice of parameters and the ansatz and cost function, and typically if you use local cost function, which is very similar, you can avoid that in practice, right? So essentially you have your ansatz, you can prepare your right hand side, you can compute your, if you can compute your cost, you can optimize your theta, which encodes your solution to this linear system using a classical method, right? So that's the variational quantum linear solver. So again, A is non-unitary, right? Like coming from a discretization of PDE. So we have to decompose it in form of a linear LCU, but here we can use our sigma base as linear combination of non-unitary decomposition, right? And then we can express these cost functions, which I showed here, in terms of computing these terms beta ij and gamma ij, which depends on these decomposition terms. And for local cost function, you have to additionally compute this term. So all these terms, as you may recall, look like terms of this form, and we have already discussed how to construct quantum circuit to compute those observables, which will give you the values of this gamma ij, beta ij, and delta ijk, right? So as soon as you have those values, you can compute these costs, and then you can optimize them on a classical computer and do the full loop, right? So thing to note is that how many terms you are getting. Your number of terms in this decomposition scale as NL square, where NL is the number of terms in your Pauli Pauli or sigma basis decomposition, and N times NL square Hadamard test. So that's why you really need to have a smaller number of L, otherwise you'll have a very large number of terms to compute the cost each time and then optimize, which can actually become a bottleneck. So let's see. Okay, I think I am running kind of slow on time, so I'll not go into this, but we actually, using this formulation, we developed a PDE constraint optimization framework, and these are the papers listed. And as we were doing that research, we realized this Pauli decomposition became a key bottleneck. And then really sigma basis is when we started exploring that idea. And we showed that by using that, we can speed up the computation significantly because the number of terms you need to estimate it can be made significantly efficient. Okay, so in last 1 or 2 minutes, I'll just talk about now moving to block encoding. So we were talking so far about variational quantum algorithms, right, where you have to sample many circuits or do many Hadamard tests to compute expectations. In a fault-tolerant algorithm, you get that action of A on psi in one shot, right? And we saw that through PEP and cell oracles, which I just list here again. And this circuit, you can actually, given an LCU decomposition of matrix, can compute the block encoding of your matrix A, right? And this is just a conceptual circuit, but this paper actually worked out actually how many resources you need in terms of, H, S, T, and C naught gates. So that's why it's Clifford plus T complexity. And this is the number of estimates here, which lists the number of ancilla, what's the gate count, and what's the depth. And that depends on, so I think without going into detail, the thing to note is they all depend on NL here, right? So smaller the NL, the number of terms in your Pauli decomposition, more efficient this representation would be. So we can now, how do we use sigma bases, right? This assumes that you have decomposition where each of the terms in the operator is already unitary, right? When we decompose our matrix, the AL terms are non-unitary, but we can still define tensile operators when AKs are now formed from tensor products of sigma bases, which are non-unitary. And luckily, there's this notion of block encoding, which says that if U1 and U2 are block encoding of A1, A2, then this circuit actually constructs a block encoding of weighted terms of A1 plus A2, right? So this circuit is actually very similar to this. The only thing you'll notice is there's more needed to implement the unitary completion or or block encoding of each of those matrices, right? So you have to add those additional bases, but then by using that, we can construct a sigma basis based block encoding, and assuming this number of terms depend like linearly on the size of the matrix, while polylogarithmically in sigma basis decomposition on the size of the matrix, and using similar analysis, and you can find the details in the paper, we can actually get an exponential reduction in the gate count and the circuit depth. Again, looking at this table, if n reduces to log n, then you get an exponential reduction in the resources you need for implementing this way of block encoding. Okay, so I think I am now getting to the end of this presentation. So in this work, we explored these non-unitary sigma bases for LCU type decomposition, and LCU, which is a key data access model in many quantum algorithms. And hopefully I gave you sufficient examples to motivate why it's a good idea. Again, it depends on your specific problem and structure, but it could give you this efficiency. We presented an efficient numerical semi-analytical techniques to decompose any given matrix in the sigma basis decomposition, and we also constructed an efficient quantum circuit using the concept of unitary completion. And through several examples, we showed, you can exponentially reduce the number of terms in your decomposition, but that comes at a slight increase in cost, like you needed one more additional qubit, few more gates, and a slightly increased depth, which all logarithmically or log dependence on the size of your matrix, which is not that significant, I would say, compared to the exponential reduction you get in your number of terms. And as we showed, this has a significant implication both for variational algorithms, where you can reduce the number of your circuit runs with a slight increase in the depth of your circuit, and fault-tolerant algorithm LCU-based block encoding, where you can exponentially reduce your gate count and circuit depth, right? So and the last thing I want to say, so we're calling this sigma basis things, right? And we chose sigma bases as our things to combine to form and get an efficient representation of sparse structure matrices. But this is, I think, a more general, and we think, right, I mean, I think is a more general paradigm of decomposing your operators as linear combination of things, where you can choose and be clever about picking things which give you an efficient representation. And you'll see, as I mentioned earlier, a talk maybe in a week, where by introducing other things into the sigma bases, which are permutation matrices, you could gain further efficiency. So if you're creative in your application, you may be able to exploit this concept more generally, and hopefully you find use of this method in your application. So, I refer to one of our papers, but there is extended version that will appear soon. If you check by this name on the archive, you'll see this, or if you send me an email or to me or Vinaya, we can happy to share that. And then I'll just thank DARPA for partially supporting this research. And with that, thank you for your attention, and happy to take more questions if there are any.
Hi. Yeah, thank you so much, Amit. It was a great talk, a lot of examples. I have a few questions coming in on Discord, so let me read it out for you. We have a question from Gerardo Suarez. Do you know, I mean, it's kind of going back to your example. Can you explain the difference between unitary completion and dilation with some simple examples? And following up on that, does unitary completion only work for the SU and matrices, the special unitary group of matrices?
Yeah, great question. So yeah, I skipped through this slide kind of quick, but I've been chime in as well, right? So yes, as you say, right, so unitary dilation is a more general concept. If A is a contraction, so its L2 norm is less than 1, you can define the unitary dilation. But if you think of unitary completion, the U has to act on a subspace and preserve the inner product, right? Which is more restrictive condition than this more general definition, right? So you're right? The unitary dilation is more general. Unitary completion has that additional constraint. And in terms of with the sigma basis, right, this is not a general result. You can work out the unitary completion by using some properties of the sigma basis and show that that's equal to implementing this unitary, right? And we show in more general result in a paper that, like with a simple example just shown as you asked, right? So say you have one term sigma minus. If you do a unitary dilation and work out this matrix, you will need 3 C0 gates to implement this simple operator versus just one C0 gate in our approach, right? So it's just the special structure of our sigma basis, which allows us to get more efficient if you use unitary completion compared to dilation. And Abhinav, feel free to chime in if you want to.
Yeah, no, I agree with you. I think like, in order, dilation is just in general, it's more general. Like as long as there is a contraction, you can compute the dilation operator. Whereas for completion, in order to complete something, the original thing that you're starting with kind of has to already be partly unitary. Like, so in our examples of like what the sigma basis is, you can see that like just the one non-zero column we have is already like
Yeah,
a
that's right.
unitary column, right? So that's why we can extend it and complete it. So that is that limitation. So it's in general, it's more restrictive, but in the cases where it applies, we think it's going to be a better technique than dilation. Okay. So there are like a couple of questions on links to the paper. I shared the conference paper with you, and the extended version of the paper is coming soon. And when we share the slides, we will share the link to the paper with you guys. I think one more more basic kind of question on one of your earlier slides. What is like, can you kind of explain again, like what is the difference between LCU and LCNU, and why do we need to have the sigma basis decomposition?
So we go back, LCU is essentially taking a matrix A and writing it as a sum of unitary operators, because we know we can only implement unitary operators on a quantum computer, right? So each of this term is a unitary matrix, right? But LCNU, we are saying that these terms doesn't have to be unitary, they can be non-unitary, right? So still you're writing your matrix as a linear combination of matrices, each of which non-unitary form from the tensor product of these sigma bases decomposition sigma basis, which are non-unitary operators, right? So it's essentially, yeah, it's linear combination of unitaries. You're taking some of unitaries here, we are taking some of non-unitary matrices, and that's why we call it LC and U. And regarding the question, why is it useful? So like maybe we look at this simple example again. You have a matrix with zeros everywhere. It's a 4x4 matrix with two non-zero entries, right? If you write this matrix as a LCU in terms of Pauli basis, which is sigma x, sigma y, sigma c, you get these four terms, right? But if you do sigma basis, which has this particular structure, you can just write that matrix in terms of two terms, right? Which is what you should ideally maximally kind of need, right? Because there's only two non-zero terms here, right? So basically Pauli basis is useful like in quantum chemistry, where you often already given a Pauli basis type decomposition, but like matrices which arise in PDEs, ODEs, if you work in that space, they have this special structure, sparsity and diagonal, block diagonal, for which, as we showed through these several other examples, you can get, much lower number of terms if you use those LCNU, right? So hopefully that answers your question. But again, this is not general. It will depend on your specific application. So if those matrices have those special structure, you can exploit sigma bases. And as I said at the end, if you're clever, you come up with your own basis. Doesn't have to be this. As long as it's complete and has certain properties, you may be able to get efficient decomposition. But the trick again is that you're going to reduce your number of terms. You should not come at an expense of increased quantum resources for implementing those non-unitary operator, right? So that's the trade-off here. You can get compression, but somehow that would be not useful if you need very large circuits to implement those unitaries, right? So as long as you can play in that space, you may be able to come up with your linear combination of things and exploit that in your problem, right? So that's the general concept we're trying to say here, and illustrating it through the sigma basis for the special sparsity and structure that appears in PDE. Hopefully that gives you intuition.
Yeah, thank you. Kind of follow-up question on the discussion that we were having earlier on dilation versus completion.
Yes.
It's just one simple question. You can always find a dilation operator. Can you always find a completion?
I guess no, right? Because we said this U should also already be unitary as in the subspace, as Abhinay was saying, right? So if you go back to like these operators, right? So if you look at these, 0, 0, right, doesn't preserve inner product, 1, 0 preserves, right? So there's a subspace where it preserves the inner product. So as long as there are some terms in your basis which preserves inner product, you can always do a unitary completion. It's not unique, but you can always do that, as that theorem says, right? So it has to have that additional property, right? That it preserves inner product on the subspace, which was true for these sigma bases, and so we could use that and get better resource estimates.
Yeah, yeah, thank you. So can LCNU decomposition be done on a matrix with bad condition number?
Yeah, I mean that is always possible, right? You can always write a matrix as a sum of unitaries. The bases you're going to choose, either the sigma bases, Pauli bases, have to be complete, right? So when you take tensor products of these terms, you should be able to get any entry in that matrix, right? So a general matrix can always be written. Now, whether it's, yeah. So I think that can always be done. Yeah, I mean, if it's ill-conditioned, what implications it have will depend on your end use, right? What do you want to do, right? That may still be the case, but theoretically you can do that. It doesn't matter. It doesn't depend on the condition number of your matrix. But that may be an interesting question. If it's ill-conditioned, what happens, right? In more general use of LCU in variational quantum algorithms or fault-tolerant algorithms, as we discussed, right?
Yeah, I think in general, just the data loading part, the data access part itself does not depend on the condition number. But it depends on what algorithm that you use, like a HHL algorithm or VQLS. Those particular solvers would depend on the condition number, but not the data access part itself.
Yeah.
Thank you. So one more question. So do these concepts describe how and why a quantum computer works?
This concept describes
Yeah.
well, I guess, I mean, we didn't get into how quantum computer works, but we know what it takes to work, which is this unitary. We have to ultimately get everything in form of a unitary to implement on a quantum computer, right? And so that's why we have to do all this work, because they, again, obey the laws of quantum mechanics, which evolve according to those unitary operators. So we are restricted to that space. Anything we on a computer has to be mapped in form of an ultimate unitary, which will take your state, apply that unitary, it will generate a quantum state, and then you apply right measurement protocol to get your solution you're interested in. Right. And also in quantum computing, right, it's really the algorithm is the secret sauce. The quantum computers are not fast in terms of number of flops. They're actually very slow. But really, if you have a better quantum algorithm, which better complexity, then you will have a hope to get better advantage over classical methods, right? If you don't have a algorithm which is more efficient than a classical algorithm, the best algorithm, quantum computer is not going to help you, right? So maybe that's one thing to keep in mind.
Yeah, thank you. That was a nice answer that answered this broad question.
Yeah.
I think that's all oh, wait, there is a follow-up. So I saw concepts like C naught, which I think relates to circuits. Yeah, so that's why the person was curious about asking that question.
Yes.
Yeah, okay. Yeah, I think that's all the questions we have from participants. Maybe one final question from me. So in general, if a person has their own problem-specific, PDE that they want to solve and they want to use this technique, where do you suggest that they start looking into, and how do they approach their problem?
Yeah, so that's an interesting question. So I would say, hopefully these examples give you some template, right? So when you discretize your problem, you're going to get this linear system, right? If ultimately that's the problem you are interested in, for example, right? And if you actually, let me bring to the general method. So if you have some kind of a repetitive structure and sparsity, you can maybe, that's a good indication that this type of approach may be helpful, right? So that's the first thing, right? You have to look at your matrix, and if there's some kind of recursive structure with some sparsity, maybe that's when you may want to start, right? So as we described, right, you can take your matrix and use these methods to decompose, right? So you get your terms AL, in your decomposition, and then you can compute observables, or you can directly embed in a fully fault tolerant method if that's what you're interested, using like an LCU type method to do other things, which is ultimately what you want to use this for, right? So yeah, I would say look at the problem, look at the structure, and if there's a pattern and some sparsity, then this method may be worth exploring. And maybe you can further, if there's some other special structure in your problem, you can be clever and add other basis elements in your sigma basis, which can help you further get efficient representation, as long as you have efficient ways to implement that terms in terms of circuits, right? So this is a very general framework, I would say, right? But again, whether it's going to be useful depends on the problem at hand, and so you have to look at that, and hopefully these examples give you like when this may be useful, right? I mean, that's all I can say.
Yeah, thank you so much. That was
Okay.
great. Yeah, thank you so much for taking the
Yeah.
time to come and talk, share your insights on this with everyone. We really appreciate it. Thank you once again.
Yeah, thank you again for inviting and the opportunity to speak and present our exciting work. Hopefully you will find it useful in your work and further build on it. There's a lot of open questions here, right, too.
Yeah. Thank you so much, Amit.
Okay.
And yeah, with that note, I would like to highlight like the next session that we have this week. We are going to look into one other key problem that we need to solve in terms when we talk about algorithms for differential equations, which is, the fundamental problem is nonlinearity. Like, how do we efficiently handle nonlinearity? And so for this, come on Wednesday, we have a talk by Dr. Pedro Costa from BQP. He's going to talk about how do you solve quantum algorithms for, how do you develop quantum algorithms for nonlinear differential equations. I highly recommend that. And kind of building up on its talk, next week we have talked by Dr. Rubin. So he's going to talk about how the quantum computing can be used for weather modeling applications, and he's going to talk about extending the work that Amit just presented, and addressing this problem of data access models. And you can see how he has extended this work even further for his specific application. So yeah, thank you everyone for tuning in today, and I hope you had a very informative session. Thank you once again. See you on Wednesday.